Hello, it's Stat 135, Lecture 15. Last time we were doing section 9.2 on frequentist frame hypothesis testing. We've seen the alpha and beta type errors, the likelihood ratio test, which says reject the null if the ratio of the null distribution to the alternative distribution is less than some constant c determined by alpha. The power, which is 1 minus beta, which is the probability that you reject the null when the alternative is true. We've seen the Neyman-Pearson lemma, or NPL, which says that the likelihood ratio test is the most powerful for any simple hypothesis. So today we're going to finish section 9.2. We'll review the likelihood ratio test and power. We'll see what uniformly most powerful tests are as an extension of the NPL to composite or non-simple hypotheses. And we'll also see what a power curve is. So first, review of LRT and power. Say that x is exponential lambda. Remember the density for exponential. And say that we have just simple hypotheses that the null is lambda is 1 and the alternative is lambda is 2. Say that alpha is 0.05. And let's ignore for now this lambda being greater than 1. We'll get back to this in a minute. So what's the LRT and what is the rejection region? So this is something you can determine without doing any calculations. You just need to draw the null and alternative distribution and look roughly which side of your x-axis we need to look at for the null distribution to be higher than the alternative distribution, which is clearly on the left side. So that's going to be our rejection region. So we know that we're going to be rejecting for x less than k. And what is precisely that cutoff we can compute by writing alpha is probability that we reject under the null distribution, the probability that x is less than k, which is the integral from 0 to k of e to the minus x dx. E to the minus x is the null distribution. So we get that k is 0.0513. Now you could have done this also without thinking and just doing this in terms of lambda, and you would have gotten exactly the same thing, but I think it's much wiser to try and graph the distribution, so because we know the null and alternative distribution is functions of x, not right now we don't know the distribution of gamma. That will come in section 9.5. So now for alpha's 0.05, what's the max power that we can achieve among all hypothesis tests? Well, the LRT tells us that it's the Neyman-Pearson lemma tells us that LRT is the most powerful, with alpha is 0.05, and that power is 1 minus e to the minus 2 times 0.053, just using the definition of power. So now a uniformly most powerful test, or UMPT, this applies when our alternative is composite. And so a test is UMP if the LRT gives the same rejection region for every simple alternative. So for example, if x is a single observation from the probability density function given by the Laplace distribution, let's start off and just find the most powerful test for the null theta is 1 and alternative theta is a half. So we can just look at this picture, ignore the blue curve, just look at the red and green curve. You can see that the rejection region is going to be in the tails because in the center the null distribution is higher than the alternative distribution. So we would accept it there. So to find exactly what the cutoff is, we'll have to make a calculation. But our LRT is reject the null if the absolute value of x is greater than k. And so we can find k just by definition of alpha. And we get that k is 3. So that is the cutoff. And right, so the LRT is reject H0 if the absolute value of x is greater than 3. So next we're going to see if this test is UMP for the composite hypothesis, where our alternative is going to be theta is beta, is b, a number between 0 and 1. So we can see from the picture here that for the alternative between 0 and 1, just look, for example, at the blue curve, which is theta is a quarter. You can see the trend that H0 will always be higher in the middle than H1 for any theta is b between 0 and 1. So our rejection region will always be in the tails, and because the definition of alpha just involves the null distribution, doesn't involve the alternative at all, you can see that k will be exactly the same. K is not dependent on, k is not a function of b, as long as as long as b is between 0 and 1. So the rejection region is the same for all b between 0 and 1, and hence the test is UMP. Now note that when b is greater than 1, our rejection region changes, right? Because when b is greater than 1, now the green curve will, in the center, will be higher than the red curve. And so now we're going to reject in what was before the acceptance region. We're going to have a swap. We'll have to find out what that cutoff is, and we'll do that in a moment. So, but you can see now that our LRT is we're going to reject H0 if the absolute value of x is less than k. And so you can just calculate here. Right, so you can just calculate here that alpha is 0.0513. So there we are. So I don't need this. So there we are. And okay. So now the LRT says reject H0 if the absolute value of x is less than 0.0513. And so the test reject H0 if absolute value of x is greater than 3 is only UMP for alternative for b between 0 and 1, not when b is greater than 0, b not 1, right? So we have a different likelihood ratio test when b is greater than 1. Finally, so let me just mention also that you can see in this example that we did before, so if for example, lambda is greater than 1 here, if lambda is greater than 1, right, so if lambda is greater than 1, we're always going to have the same rejection region. You can just see it in the picture here. In this picture here, we have lambda equal 2, for example, and you can see that the y-intercept is 2, so the y-intercept will always be higher than the null distribution when lambda is greater than 1. So we'll always have the same rejection region, and hence the likelihood ratio test that we have will have the same cutoff when lambda is greater than 1, and hence our test, our hypothesis test with lambda greater than 1 as the alternative will be UMP. So finally, we talked briefly about the power curve. This tells us the power of our test for different theta, and so for example, what is the power for any theta greater than 0? And well, when theta is between 0 and 1, you can show here that the power is exponential minus 3 theta. When theta is greater than 1, you have 1 minus exponential minus 0.051 theta. And of course, when theta is 1, then the power is just alpha. Because when theta is 1, the alternative is the same as the null distribution. So we just get the definition of alpha in that case. So here you see a typical power curve where it goes down and then it goes back up to 1. Great, I'll see you guys next time.